Howdy. The purpose of this video is to introduce a few different kinds of point defects that we commonly see in different materials. Now, why do we care about point defects? Well, there are at least three different reasons. First of all, point defects can influence the structural properties of materials. So one way to strengthen materials is to do what's called solution hardening, where we dissolve a bunch of single point impurities in the material, and this changes how the material is able to deform. And so you can strengthen a material that way. Another reason would be if we're interested in electronic properties. So in this case, it's usually referred to as doping, but you can control the number of charge carriers and what type of charge carriers they are in a system by controlled doping of different electron donors or acceptors in a system. Finally, we might want to control the motion of point defects throughout a material. So this is the case in a fuel cell where we need certain atoms to migrate from one side of a material to another side. So we want to make it easy for there to be vacant sites for these atoms to move along in. Okay, so what are some of the different kinds of point defects that we might see? We're going to first consider the metallic systems. And there are three basic kinds of defects that we're going to talk about. The first is called a vacancy. So if this is our lattice here, if one of these atoms was missing, it's not there, that is what we call a vacancy. Now I'm going to show you the notation for these different kinds of defects as well. So if we have a vacancy, we symbolize that V for vacancy, then we say what the atom was that is missing. So it was on an aluminum site, say. So this aluminum site is gone. And then we give a symbol that refers to the charge of this point defect. So in this case, aluminum vacancy in aluminum lattice is a neutral charge. So we put an X there. So vacancy is the first type. The second type would be an interstitial. And that is if we have some other atom sitting in a site in this lattice that is not normally occupied. So let's say, for example, this is still an aluminum atom. I'll say aluminum there. We would notate this Al. So this is now an aluminum atom, and it's on an interstitial site. That's what the I means. And again, it's a neutral charge. So we give a neutral sign. That's the X symbol up there. The third kind of point defect that we would see would be a substitution. So again, let's say this is a lattice of aluminum atoms, but this atom here is not aluminum. Let's say this is copper. So the notation for this is going to be written as such. So again, a copper atom is sitting on an aluminum site, and the net charge is neutral. So these are the three different kinds of vacancies, of point defects. We have vacancies, we have interstitials, and we have substitutions. Okay, next we're going to think about ceramic or ionic compounds. And there are additional things that we have to consider in these cases. And that's just because an ionic compound has positively charged ions and negatively charged ions. So let's say each of these blue is a cation, and each of the red is an anion. And for the purpose of this, let's say these blue are magnesium, so it's actually +2. And the red are oxygen, so it's -2. So in the ionic case, we can't simply have a vacancy of one of these atoms because that would lead to a charge imbalance in the system. Similarly, we can't just have a substitution of one other charged species in the lattice because that would also lead to a charge imbalance. So the rule is that when we're dealing with ionic compounds, we always need to maintain charge balance. Because of that, there are two special kinds of point defects that we see very frequently in ionic systems. The first are called Schottky defects. And this is when we have a paired vacancy. So let's say both this magnesium and this oxygen atom are missing. So we're missing a +2 charge and we're missing a -2 charge. So we have maintained charge balance. The notation for this I'm going to write it first and then I'll explain what it means. Okay, so I've written it like a reaction. So initially we have the pure lattice, but we went to the case where we have a vacancy of a magnesium cation and a vacancy of an oxygen anion. Now you'll notice I didn't put an X up here because both of these are charged species. Magnesium has a +2 charge, so if we have a magnesium vacancy, that means we have a -2 charge because that +2 that is usually there is not there. So -2 charge is written by 2 dashes up here. Similarly, a vacancy of an oxygen would have 2 positive charge, so we notate that by 2 dots up here. So this would be a single magnesium vacancy, a single oxygen vacancy, but again, the Schottky defect is where we have the case of the paired vacancies. Now there's another way that we can maintain charge balance, and that's instead of removing a charged, a positive and removing a negative species, we could remove a positive species, but then put it somewhere else in the lattice. So again, let's say these blue are our magnesiums. So let's say this magnesium atom leaves its normal site and comes to sit here in an interstitial site. So this is what we call a Frenkel defect. I'm going to, again, I'll write out what the reaction looks like and then I'll explain the notation. So originally we had a magnesium on a magnesium site, and that was not charged. And again, I write it as if it were a chemical reaction. I now have a vacancy on the magnesium site. So magnesium is 2+. The magnesium vacancy would be 2-. And they have a magnesium on an interstitial site. So the magnesium now is 2+, and because it's on an interstitial site, we say that has 2+ charge. So one of the things you note, you can see with this notation is that the charge on both sides of the reaction is equal. On the left side, we have neutral, no charge. On the right side, we have -2 and +2. So again, it comes out to be neutral. Okay, so in review, we talked about the 3 different types of point defects. We have vacancies, interstitials, and substitutions. And then also we talked about the special rules that you need to follow in ionic cases. And really these are all centered around the concept of maintaining charge balance. Finally, I showed you some of the notation for these point defects.